Let's talk today about the structure and isomerism. Now, let's talk about initially the word called isomers. And when we talk about the word called isomers, here we have the word iso, which means same, and meros, which means parts. The various compounds which are made up of same number and kind of atoms are termed as isomers. Here you can understand that I am saying that the various compounds, that is, these are different compounds, but they have a similarity, they have a common thing that they have the same number and kind of atoms. When we talk about isomers, they are different from each other. The aspect in which they are different from each other decides what kind of isomers they are. Dominantly, we divide the isomers into two categories. One, structural, and other one, stereo. The stereoisomers can be termed as stereomers, stereoisomers, and structural isomers are also termed as constitutional isomers. When we talk about the structural isomers, organic chemistry, the structural isomers are divided into five parts. The first one, chain, position, functional, metamers, and the ring chain isomers or ring isomers. When we talk about the stereoisomers, these are mainly divided into two categories: configurational and conformational. The conformational isomers are termed as conformers, conformational isomers, conformations, skew isomers, or torsional isomers. So these are the name for the conformational isomers. When we talk about the configurational isomers, we have two main categories. One is termed as diastereomers, other one is termed as enantiomers. The diastereomers are further divided into two categories. One is geometrical diastereomers, and other one is what we termed as optical diastereomers. Most often, geometrical diastereomers are simply termed as geometrical isomers, and many times people don't even realize that geometrical isomers are actually diastereomers, while we have optical diastereomers. Now, these are the categories of isomers. Now, we are going to do detail of each of these categories and the definition of it. To begin over, let's start with the simplest, hydrocarbon. Now, when we talk about the word hydrocarbon, these are binary compounds of carbon and hydrogen. Or we can even say these are hydrides of carbon or whatever they are. Binary compound actually means that these are compounds which contain two kind of atoms. Please remember there is a word called diatomic. Diatomic means a compound which contains two atoms in each molecule. So binary compounds we are talking about. There could be any number of atoms, but there are only two kind of atoms. So hydrocarbons are binary compounds of carbon and hydrogen. Now, when we talk about hydrocarbon, the simplest hydrocarbon is what we know as CH4. Now it is termed as methane. Please remember, methane is not the systematic name. The systematic name of methane would actually be carbane, but I don't know. You might not even have heard of this particular name because it's not used. It's not your fault that you have not heard of it. It's not used. It's just a systematic name. But chemistry talks about the names which are more easily understood rather than systematics. Now, methane is a historic name. It's the common name which has been accepted in the IUPAC as the IUPAC name. When we talk about methane, now we have come to understand that whenever we are using meth, it would denote one carbon. So any compound which contains only one carbon has the word root as methane. Like we could have methane, we could have methyl chloride, chloromethane, we could have methanol, we can have methanoic acid, we can have methanol, we can have any compound which has one carbon would be termed as meth. So we understand the myth as the word root. Now we talk about the representation and the structure of methane. Simple as that, we could have the expanded formula, the formula which gives us the linking of methane. It just tells us which atom is attached to which atom. It does not actually talk about the various arrangement of the atoms. It does not give what are the angles and so on. So this is a very simple, very straightforward formula, very straightforward representation, which simply gives us which atom is attached to which atom. But then we understand that methane is not actually a planar compound. It is a three-dimensional compound having an angle between carbon, hydrogen, and carbon. And this particular angle, when we talk about the observation and the various consideration, tell us that this angle is actually 109 degree 28 minutes, which is generally represented as generally written at 109.5 degrees. Now, how do we represent a three-dimensional structure in two dimension? We do not actually draw the structure. We actually write the structure. Please remember, whenever we have a symbol, like we write something like A. Now, what exactly is this symbol? Does the symbol tell you that this is going to be uh, spoken as A? No, it doesn't. It has been told to you that the symbol means A. In various languages, like in German, it would be called A. In English, it's called A. In Hindi, A would be a different symbol. So that simply means these are conventions. These are not actual things. So here, in the same manner, we write the three-dimensional structure rather than drawing it. While writing the three-dimensional structure, we again use certain conventions. We make a symbol like this. Now, when we talk about this particular symbol, this is termed as a solid wedge. When we talk about the solid wedge is simply a representation in which the bond, the structure is moving out of the plane. It is moving out of the plane towards the viewer. So this is what we have the representation, that's solid wedge. Then we have dashed wedge. This is the dashed wedge. The dashed wedge would mean that the bond is actually moving in the plane. It is moving away from the viewer. So this is what we term as the dashed wedge. Simply speaking, simply put, we simply call this solid wedge as wedge and this dashed wedge as dash. Whenever we are using this particular representation to give the structure, three-dimensional structure of a compound, we call it wedge dash representation. Then we have a simple solid line. The simple solid line simply means that the bond is with the plane. That is, it is parallel to the viewer, not moving towards the viewer, not moving away from the viewer. Many a times, we simply represent that solid wedge as this while writing it. We don't even fill it. We simply make it in this manner. And the dashed wedge, we don't talk about the bond being have the line being small and the large and it's going as a wedge. We simply write it this way. This also is acceptable. The solid wedge is simply written as a elongated triangle, and dashed wedge is simply written as the sequence of the lines. You might encounter this kind of a structure. Now, people think that this kind of a structure would actually be a way to write the dash, but this kind of a structure actually has in itself a some meaning. This meaning is don't know. Now, it doesn't mean that I don't know the meaning of this particular representation. It simply means that this representation actually means don't know. If you do not know whether the atom is moving in the plane, whether it's the atom is moving out of the plane, or whether the atom is in the plane, on the plane, we write this particular representation. This representation is mainly used to ask questions. They would give you a structure in which one of the bonds would be represented by this thing, and they would ask you what would be the actual representation. Will the bond be moving out of the plane, whether the bond would be moving in the plane, or the bond would be on the plane. So that is the representation where we actually do not know, or we want to ask where is the atom actually lying. So if we talk about this particular representation, the methane would be represented like something like we have this, this moving out, that's moving out, and that's moving in. This is how methane is a representation in a wedge dash representation. Now there is another way to represent in three dimensions without actually making even wedge dash. What we do is we raise these bonds a little higher so that the structure would become here it's moving up as wedge dash. Here it's moving out of the plane, and here it is again moving back. Now remember this angle is 109 degree 28 minutes, which is normally written as 109.5 degrees. Before we get any further, could anybody please tell me how many 109 degree 28 minutes or 109.5 degree bonds are there in methane? Count it off. If you have mathematics with you, then in that case you can actually use the permutation and combination. Here we are talking about combination. It's going to be NC2. That is, we are going to talk about the number of atoms attached to a given atom, that is N. We are going to talk about combination, and we are taking two atoms at a time to define the angle between them. So if we talk about simply the formula, N is 4 factorial, then it is the N minus 2 factorial and 2 factorial. This is going to be 4 minus 2 factorial into 2 factorial. That would turn out to be 4 into 3 into 2 into 1 divided by 2 into 1 into 2 into 1. And if I cancel it out, it turns out to be 2 and 2 gone, 2 and 4 gone, 2, and it becomes 2 into 3 is equal to 6. So this is the formula which gives us the number of angles. And I hope you remember the permutation formula. And if you don't remember it, it's going to be NCR is equal to N factorial divided by N minus R factorial into R factorial. This is what we have as the formula. Well, I won't go into mathematics more than that. This much is enough as far as mathematics is concerned. But there are six angles in this particular compound. And you would be saying, how do we understand that there are six angles? Now you can see this is one angle I have already marked. This is the second angle. This is the third angle. Then this would be the fourth angle. This would be the fifth angle. And this would be the sixth angle. So there are actually six angles of 109 degree 28 minutes in methane. Fine. Now let's talk about this particular representation here. In this representation, the top and the bottom are moving away from the viewer and the sides are moving towards the viewer. Now, it is a very strict convention that the top and the bottom have to be moving away from the viewer and the sides are moving towards the viewer. In chemistry, whenever we perfectly know that what we are trying to tell is already known by the person, we don't actually tell it. So, if we know that the top and the bottom are moving away from the viewer and the sides are moving towards the viewer, we won't actually tell it. We would consider that the viewer already knows. So, we simply write it in this manner. We simply write it as the solid lines and we leave at that. The top and the bottom are moving away from the viewer and the sides are moving towards the viewer. This is understood. It is not to be told. And this kind of a representation, this is a three-dimensional representation of a compound in two-dimensional, and this is termed as the Fisher projection. This is what we term as Fisher projection. So this is how we can represent methane in three dimensions. Now you have to remember these conventions because these conventions are what are asked in the examination many times. Now once we have talked about methane, let us get along with the next compound, C2H6. And this is what we call as ethane. Now remember, ethane again happens to be a conventional or historic name, comes from ether. And when we talk about this ethane, the ethane would mean two carbons. So whenever we have an organic compound containing two carbons, whenever the two carbons are linked to each other, the word root turns out to be ith. It could be ethane, it could be ethene, it could be ethyne, it could be ethanol, it could be ethyl chloride, it could be chloroethane, it could be ethanoic acid, so on and so forth. Ith means two carbons. Now, when we talk about the structure of ethane, it is something like CH3, CH3, or we can again make the detailed structure H, H, C, H, H, H. So this is what we have as the structure of ethane. Now, to make the ethane in wedge dash, of course, we can make it in three dimensions. Here it would be here. This is the wedge dash representation of ethane. Now, we being lazy people, we would prefer that we do not have to make in such a deliberate or such a extended version or such a detailed version. What we simply do is we take the ethane a little sideways. So we have the molecule in which there is first carbon here. Here we write it in this manner. This is the first carbon. And we take it here. This is the second carbon. Now, if you talk about this particular structure, what we find is that we can actually make a structure over it like this. So if we talk about this particular structure, and we remove this part, this structure is termed as a sawhorse. So this is the sawhorse representation of ethane. This again is a three-dimensional representation, but here again we have done away with this wedge and dash. We are simply making this particular representation. We are simply writing this representation. This is the sawhorse representation. Now, if we have the ethane molecule being looked from the front, that is, we have the carbon behind each other. So we have the front carbon like this. The hydrogens would be like this. The front carbon, the hydrogen would be actually moving towards the viewer. But here we have represented it with a straight line. This is the front carbon. Now, the carbon behind it won't be visible. But if you look at a little side, then the hydrogens would be visible. So this is going to be one hydrogen. This is going to be another hydrogen. This is going to be the third hydrogen. And this particular representation is termed as the Newman projection or the Newman representation. So this is a representation of ethane in three dimensions when the two carbons are one behind the other. So this is what we term as the Newman projections. And then quite obviously, we can just lift up the two hydrogens, making it straight. Thus, carbon would be straight in the plane, while the hydrogens would be above and below the plane. So we could just make it in this particular arrangement. Here we have the wedge, the two hydrogens like this, the third hydrogen like this, again the two hydrogens on the top carbon like this, and the third one like this. Now, this is what we call as Fisher projection. So this is the Fisher projection of ethane. So that is how we can represent the organic compounds, the hydrocarbons, and various other compounds in three dimensions without actually drawing them, just by conventions. Now moving on to the next compound. Here again we have C3H8. Now this particular compound is termed as propane. When we talk about the propane, here we have, of course, we can write it in this manner, 3 hydrogen, 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 hydrogen. It's quite boring writing all these hydrogens. And we do understand that carbon has a valency of 4. If we get a compound of carbon in which the valency of carbon doesn't seem to be satisfied, we can actually put the required number of hydrogens so as the valency of carbon is satisfied. Now, we do understand that hydrogen is going to satisfy the valency of carbon. And when we know that hydrogen will be satisfying the valency of carbon, we don't actually need to write hydrogens. We can simply consider that hydrogen are not there, or we can consider that whatever is the number of hydrogen required, you can easily put it. So why do we need to write the hydrogen? Why can't we simply put the carbon skeleton? And it's already understood that these three carbon, the valency is satisfied by the hydrogen. The first carbon has one carbon attached to it, and there are three hydrogens remaining. So we put three hydrogens with the first carbon. The second carbon has already two bonds with it. So we need to put two other hydrogens. And the third carbon has, again, one carbon attached to it. So three more hydrogen need to be put. This is what we term as the simple thing, and we can talk about it here. So we don't need to put hydrogens here. So we can simply put the skeleton, and then somebody would argue that we already know that organic compounds contain carbon. So is it not required to put carbon even? Can we make the structure of organic compounds without even putting carbon? And the answer is very much yes. We can actually consider that simply we put the bonds, not even the atoms. Here, this is one bond, and here it's another bond. These points, they would represent carbon. So in actuality, it is not required to make carbon and the hydrogen attached to carbon while representing the organic compound. This is what we term as the bond line structure. Now, bond line structure is the least informative of all. It is actually confusing because if you don't make the actual structure, you don't even know how many carbons could be there and how many hydrogens could be there. And we have to put all the other atoms, and there is a confusion if we simply write it here, we write it OH. Now remember, the hydrogen attached to any other atom other than carbon has to be mentioned. So if we put it OH, in this case, this particular compound does not have three carbon, it actually has two carbon, and the third position is occupied by oxygen. So it is much better to convert the bond line structure into the at least the skeletal structure, at least the carbons, before you try to give the name. Otherwise, it's a large chance that you end up giving a wrong name. So this is how we represent in the bond line structures. Now, many a times it so happens when we're talking about bond line structure, we are not writing the hydrogen. So there is a possibility that we might miss the double or the triple bonds or maybe the cyclic structure, because bond line structure doesn't tell whether the hydrogens have been balanced or not, all the hydrogen have been accounted or not. So we need to know in advance whether the compound is going to contain a double bond or not, or a triple bond or not. And here turns out to be a simple way to find out whether the compound contains double and triple bonds or not. And this is what we term as the double bond equivalent. Double bond equivalent. And this is also termed as degree of unsaturation, or it is also termed as hydrogen deficiency, or maybe whatever you would wish to call it. There is a formula to determine the double bond equivalent or degree of unsaturation. This formula says summation n bracket V minus 2 divided by 2 plus 1. Now here V is the valency of an atom, and N is the number of atoms having that particular valency. For example, let's talk about a compound C3H8 only, propane. Here we have three carbons. The valency of carbon is 4 minus 2 divided by 2, plus we have 8 hydrogen. Valency of hydrogen is 1 minus 2 divided by 2 plus 1. It turns out to be 0. If the double bond equivalent turns out to be 0, degree of unsaturation turns out to be 0, this would mean that this particular compound does not contain any double bond, it does not contain any triple bond, and it does not contain even any ring in the structure between any atoms. It is not necessarily that the double bond, triple bond, and the ring has to be formed by carbon. There could be any other atom, something like if we say the double bond equivalent is 0, that would mean that there isn't even carbon oxygen double bond or carbon nitrogen triple bond. They also do not exist. No triple bond, no double bond, no cyclic structure in the entire compound. That is the meaning of double bond equivalent. If the double bond equivalent turns out to be 1, it could mean a double bond or it could mean a cyclic structure, one ring. Please remember, one ring also is a degree of unsaturation. If the double bond equivalent turns out to be 2, then in that case it could be having one, two double bonds, or it could be having one triple bond, or it could be having two cyclic structures, two rings, or it could be having one ring and a double bond. Any combination is possible. Please understand, one double bond is one double bond equivalent, one triple bond is equivalent to two double bond equivalent, and one cyclic structure again is equal to one double bond equivalent. So this is how we talk about the double bond equivalent. Now, this double bond equivalent is enough to give us the number of double bonds and triple bonds in a compound or the various combinations. So we can actually make the bond line structure without worrying about the hydrogens, whether they have been accounted for or not. I would request whenever you are asked to make the isomers of a particular compound, the very first thing you do is find the double bond equivalents. Many a times it so happens that you have been given a structure and you are asked to give the formula, or you are asked to give the double bond equivalents, or you are asked to give the number of rings in a compound. In case of organic chemistry, the number of rings are not the rings that you actually count. The number of rings are the minimum number of bonds that you need to break to make the cyclic structure as a non-cyclic structure. For example, if you have this kind of a structure, if it had been an IQ question and you would have been asked how many rings are there, then the answer would turn out to be one, two, three rings. Because there could be a big ring, then there are two small rings. But if we talk about from the organic point of view, then to convert this particular cyclic structure into a non-cyclic structure, we would be having to break one and two bonds. If we break two bonds, then in that case, this particular structure does not have any cyclic structure. So this compound is actually a bicyclic compound. Please remember the number of bonds that you need to break to convert the cyclic structure into a non-cyclic structure is the number of rings it contains. So here it is, bicyclo compound. Before we go any further, let's have another question. Like let's say we have this particular organic compound. Yes, this particular organic compound is named as cubane. How many rings do you think this particular cubane contains? People might be saying that there are six faces. It's a very simple question. There are six faces, six cyclic structures. Let's count the number of rings do we have. How many rings we have? So, how many bonds, the minimum number of bonds that I need to break to convert it to a non-cyclic structure? Here goes one bond. Okay. Then here goes another one. Two. We have broken two bonds. And here goes three. And it's four. And it's five. Now, do we have a cyclic structure here? No, we don't. Cubane is not hexacyclic, it's actually pentacyclic. See? One, two, three, four, five. So, cubane is the pentacyclic structure. So, this is how we find the number of rings here. The double bond equivalent of this particular compound is going to turn out to be 5. The formula of cubane is actually C8H8. And when we talk about C8H8, this particular cubane, we can actually use the formula. It is 8 into 4 minus 2 by 2 plus 8 into 1 minus 2 by 2 plus 1. And this turns out to be 5. So cubane has the double bond equivalent as 5. Clear? It is going to be 8 minus 4 plus 1. That's 5. Now, this is what we have as cubane. Now let's get along with the next compound. Now, before we get along with the next compound, let's understand a bit more about the linkings. Let's talk about a particular compound called isooctane. Now, isooctane actually is a misnomer. We need to go on with the structure of isooctane. Isooctane is CH3, 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 CH2, CH, CH3, CH3. This is the compound called isooctane. Now, if we talk about the IUPAC number and naming of it, the main chain is pentane here. We have one, two, three, four, five carbons in a straight chain. And we have three methyl groups as side chain. So it is going to be 2, 2, 4 trimethyl pentane. That's the name of isooctane, 2,2,4 pentane. We have the main chain, the longest chain as the pentane group, and we have three methyl groups attached to it. So this is 2,2,4 pentane. You cannot just simply write 2-trimethyl because we have to give the position to each group. So whatever is the number of groups, that many positions have to be there, whether it might turn out to be the same. So this is 2,2,4 trimethylpentane. This is what we term as isooctane. Why I took the example of isooctane is that there are actually four kind of carbons in it. There are so many carbons, there are actually five carbons which are attached to only one carbon. Something like this. This carbon, this carbon, this carbon, this one, and this one. These carbons are attached to only one carbon. The carbons which are attached to only one other carbon are termed as primary or 1 degree carbon. So we have just identified the carbon, we have classified the carbon, the primary or 1 degree carbon. Primary or 1 degree carbon are the carbons which are attached to one other carbon. In this particular compound, we have five primary carbon. Now it is not only the carbon which is primary. The hydrogen attached to the primary carbon also are termed as primary hydrogens. In the same manner, if any other group is attached to the primary carbon, something like if it is a chlorine attached to a primary carbon, we would call it primary chloride. If it is OH attached to a primary carbon, we would call it a primary alcohol. So the primary carbon, any group attached to the primary carbon would be termed as a primary group, whether it be hydrogen, whether it be OH, or whether it be alcohol, or whether it be halogen. So this is a primary carbon and the primary hydrogen. In the same manner, if we talk about this particular carbon, this carbon is attached to two carbons. So this is a 2 degree carbon or a secondary carbon. While this particular carbon is attached to three carbons and it's a 3 degree or tertiary carbon. While if we talk about this particular carbon, it is attached to four other carbons and it's a 4 degree or quaternary carbon. Now, you might say that a carbon attached to five carbon would be known as pentenary carbon. Absolutely wrong, because carbon has a valency of four and it could be attached to a maximum of four carbon only. So we do not have a pentenary carbon. And in the same manner, we do not have a quaternary hydrogen or a quaternary group. The simple reason is when we talk about the carbon, if four carbons are attached to it, no other group could be attached to it. So we do not have a quaternary halide or quaternary alcohol. We do have a tertiary alcohol and tertiary halide, but we do not have quaternary halogen, halide or alcohol. So these are the positions of carbon. Now, in this manner, when we talk about primary, secondary, and tertiary, we do have some other positions as well. Something like if we have C double bond C. Now, this particular position, if a group is attached to the double bonded carbon, this particular position is called the vinyl position. So, if we have the chlorine attached to it, it will be called vinyl chloride. If we have our OH attached to it, it's going to be called vinyl alcohol. Now, if we have another carbon attached to the vinyl position and we have a group attached here, this position is called the allyl position. So this is what we have as allyl halide or allyl alcohol. In the same manner, if we have a benzene ring and we have a group attached to this benzene ring, this is what we call as a phenyl group. And if OH is attached, it's simply called phenol. Okay, phenyl chloride or chlorobenzene. And if we have a carbon attached to the benzene ring and a group attached to it, this particular position is called a benzyl. Now you need to understand that benzyl word does not represent six carbon, it represents seven carbon. So if I call it benzyl chloride, that would mean that benzene ring has a carbon attached to it and the halogen or chloride is attached to that particular carbon. So benzyl chloride actually means seven carbon. Benz, benzo, benzyl, benzal. These words actually mean seven carbons. So that's what we have as different positions and different names and different understandings. So please understand what is primary, secondary, tertiary, vinyl, and allyl. Now, getting further, we have just talked about C3H8. At this moment, we haven't talked about any isomers. We have just talked about the structure and the representation of the various structure. Now let's get along with the compound C4H10. Now, when we write C4H10, here comes out to be a little problem that we can actually make the structure in two ways. We could have CH3, CH2, CH2, CH3, Or you could simply write it as skeletal structure or bond line structure, whichever way you feel like. Now, this particular compound is simply termed as normal butane or simply N-butane. If we have to say the IUPAC name of this particular compound, the IUPAC name of this particular compound would be simply butane. This is one way to make the structure. Then the other way to make the structure would be CH3, CH, CH3, and CH3. Again, you can see all the carbons and hydrogen are accounted for. The double bond equivalent is 0, no double bond, no triple bond. So we get these two structures. Now, when we talk about the second structure, this particular structure, whenever the compound has this kind of a structure, this particular structure is called iso. So this compound has a common name of isobutane. And if you have to give the IUPAC name, it is going to be 2-methyl propane. Now, if we talk about these two structures and compare them, you can see that in the first structure, we have two primary carbon and two secondary carbon. We have two primary carbons and we have two secondary carbons. But when we talk about the second structure, we have three primary carbons and one tertiary carbon. So when we talk about these two structures, the compounds, these two structures, they differ in the linking of atoms. The linkings are changed. In first structure, the carbon is attached to one other carbon. There are two carbons attached to one other carbon, and there are two carbons attached to two other carbons. While in the second structure, there are three carbons attached to one carbon and one carbon attached to three carbons. So these two compounds, they actually differ in the linking of atoms. Of course, they have the same number of atoms and the kind of atoms, so these are isomers of each other. These compounds, they differ in the linking of atoms. The isomers which differ from each other in linking of atoms are termed as structural or constitutional isomers. So N-butane and isobutane are structural isomers of each other. Further, if we name them, and remember the organic isomerism is based on naming, the nomenclature system. If we name them, the names are going to be different. In this case, the word root in the first compound is bute. Now, bute stands for four carbons. So, the main parent chain or primary chain contains four carbons. So, this is bute. While in the second compound, the primary chain contains three carbons. That is prop. So, these two compounds they differ in the length of primary or the main or the parent chain. So since they differ in the chain length, these are termed as chain isomers. So here we have the chain isomers of butane. Getting on further, let's talk about a compound C5H12. Before we make the structure of this particular compound, it's better that we have the double bond equivalent. So double bond equivalent is 5 bracket 4 minus 2 by 2 plus 12 bracket 1 minus 2 by 2 plus 1 turns out to be 0. The double bond equivalent of this particular compound is 0, no double bond, no triple bond, no cyclic structure. Now we make the possible structure of this compound. We can simply make the carbon skeleton 1, 2, 3, 4, and 5. Now, since five carbons are in a straight chain, no branching, this is what we term as N-pentane, or simply IUPAC name is pentane. Then we could have another structure 1, 2, 3, 4, and 5. Now, as you can very well see, this particular structure would represent iso. So the common name of this compound is isopentane, and the IUPAC name would turn out to be 2-methyl butane. This is what we have as isopentane or 2-methyl butane. Getting one further, we could have another structure of C, 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 and C. Now, if we get a structure like this, CH3, C, CH3, CH3, this particular structure is termed as neo. So this is what we can term as neopentane. Now, neopentane is 2,2-dimethyl propane. If we talk about these three compounds, here the primary carbon chain is pent, and we are talking about the IUPAC name. Here the primary carbon chain is but, and here the primary carbon chain is prop. As you can very well see, these three compounds also differ in carbon chain length, the primary carbon chain length. So these three compounds also are what we understand as the chain isomers of each other. So these are chain isomers. Let us see one more compound. And here we have the compound as C6H14. Now, when we talk about C6H14, what could be the various arrangements of C6H14? We could have C, 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 and C, six carbon straight chain. Now, this is what we can term as N-hexane, N-hexane, or simply hexane. Then we could have the structure like 1, 2, 3, 4, 5, and a carbon here. This particular compound can be written as isohexane or 2-methyl pentane. Then we could have another structure 1, 2, 3, 4, 5, and the carbon here. Please remember this is not isohexane because group cannot be formed. You might say, what is the general formula or the common name of it? It might not have a common name. Every compound doesn't have a common name. So here we talk about the IUPAC name. It's going to be 3-methyl pentane. This compound is 3-methyl pentane. So this is the compound 1, this is the compound 2, this is the compound 3. Now these are not the all compounds. There are two further compound possible. Let's say we talk about the compound 4. This is going to be 1, 2, 3, 4, and we can have C here, and we can have C here. This is actually neohexane. And the IUPAC name would be 2,2-dimethyl butane. Or we could have another structure 1, 2, 3, 4, a carbon here, a carbon here. This is 2,3-dimethyl butane. And let's say this is the fifth compound. Now, if we talk about these particular compounds, we can make certain sets, like we can have 1, 2, and 4, or we could have 1, 2, and 5. We could have 1, 3, and 4. We could have 1, 3, and 5. Each of these represents a set of chain isomers. Since each of these, you can say, they differ from each other in the parent or the main or primary carbon chain. But if we were to compare between 2 and 3, they have the same chain length. 4 and 5, they have the same chain length, but they differ in the position of the groups attached to the parent chain. You can see that here we have 2 as the location or the locant or the position. Here we have 3 as the location or the position. While in these cases, we have the position as 2, 2 and 2, 3. So these compounds, they differ from each other in the position of the chains, side chains or the groups. So these are what we term as the position isomers. The structural isomers, which differ from each other in the position of the side chain, functional group, double bond, or triple bond. That is, they differ from each other in the set of locants. Locants are the numbers or the alphabets which give the position, are termed as position isomers.